Hi. So I used to talk about here about popping shells on macOS, bypassing TCC and XVC exploitation and all this stuff, but today I actually will talk about some macOS internals and some really great engineering happened at Apple. So launch constraints. My name is Csaba. I go by the evil bit on Twitter. I currently work for OffSec. I'm the lead content developer for our macOS control bypasses training. I used to be a red and blue teamer for about 8 years before, and I also do a lot of macOS bug hunting in my free time. I'm married, have 2 kids, and I'm really into running and hiking. So actually today we had a 10K run in the morning with some of the folks. It was really great. We try to make a tradition of this. So the agenda, I will quickly go through some old macOS vulnerabilities. Then I will review launch constraints, which was introduced in Ventura. Then I will review a couple of old third-party vulnerabilities, and then talk about the new launch and environment constraints in Sonoma. So some old stuff. Let's start with the TCC bypass in the Imagent app. So this was found by Adam Chester, goes by XPN on Twitter. So basically he found this app called Imagent app, which had some really nice entitlements like access to the address book in TCC and some keychain accesses. So what he found is that this application looked for plugins in its plugins directory, but there wasn't any. And the code signing properties of this application allow to load like third-party libraries. Now, the problem is that this application resides on the /system partitions. So you cannot really write there, but nothing is preventing you from copying out it to the temp directory, create your plugin, start it up, and that's it. You loaded your plugin to this application, and boom, you gained all the entitlements of the application. So this was fixed. Then we have another one. It's another TCC bypass using directory utility. This was found by Wojciech, who talked here before. Essentially, the idea is same. He found that directory utility can load plugins, but again, it's on the system partition. So, but again, you can copy it out to the temp directory or wherever you want and load your own plugin. Now, this was interesting because this application has an entitlement to actually change like sysadmin files, like perform administrative tasks on the system and also change the home folder of the user. Basically, what that allows you to do is create a new TCC DB, create a new user home directory structure, and basically update the home folder of the user to the created one, and boom, you have a new TCC database, basically fully bypassing the user part of TCC. Again, this was fixed. Next one, we keep the team with TCC. PowerDir. This was found by Jonathan Bar-Orr, who is working for Microsoft and also drops really cool bugs. So he found that there is this process or binary called config.d, which is normally a system daemon, which has the same entitlement which directory utility had. So again, it allows you to change the home directory of the user. Now, although it runs as a system daemon, nothing is prevented you to actually run it from the command line. And this binary had an option, -b, that allowed you to load any bundle. And its code signing properties allowed it to load any bundle. So you just could run config.d -b, put your dilib there, and that's it. I like logic bugs because you don't need to mess with all the memory corruptions and the stack and the heap and all this stuff. It's just way easier and usually more reliable. So yeah, this again was fixed. So Apple decided that it was enough. They were pissed off. So there is a team in this box. So they came up with the idea of launch constraints in Ventura. Basically, it's a solution to mitigate all of the previous vulnerabilities and probably many other. Well, the vulnerabilities can be there, but you can no longer exploit them, which is actually pretty cool. So they define 3 different types of constraints. One is self-constraint, which applies to the binary to the actual process. Now, there is a parent constraint, which applies to the parent process of the process. And there is responsible constraint, which applies to the responsible process of the process. So if you think about XPC, which we heard about today, then let's say the XPC service is the process itself. So self-constraints would apply to the XPC service. Now the parent process of XPC, that's launchd. So if you do any parent constraints, that would apply to launchd. But the responsible process for an XPC would be the one looking up the service and the one which is causing launchd to actually start the service. So this is the idea behind it. So we have these 3 players and 3 different constraints. Now, if we check it in action, what it does, so if we stay with the previous examples, I make a copy of find my app or any application or any binary on the system partition, I copy it to the temp and just try to run it as is. It will be killed by mv, and it will say, it just throws an error. But if we check the logs for mv, the mv logs, it will actually tell us that it's a launch constraint violation. And when I first saw that, I was like, what the hell is this? So it's launch constraints. Let's go into the launch constraints categories. A launch constraint category defines a set of launch constraints for the previously defined 3 different constraints. In Ventura, we had 7 different categories that was initially reversed and documented by Linus Henze. In Sonoma, we have now 18. And basically, what macOS does, you have all these categories and you assign a binary which is on the system to one of the categories. Now, all the binaries on your system are listed in the trust cache with their hash, and now with the trust cache version 2, you have a new field to store the category number, basically. So it's all in the trust cache. So let's see an example for a constraint category. So this is category number 1. It says self-constraint on authorized out APFS volume or on system volume and launch type 1 and validation category 1. So let's see what this means. On authorized APFS volume, it means that it's an authorized APFS volume, which I believe it refers to the cryptexes which are mounted on the system. On system volume means that it's basically under /system/library. So basically the whole partition which is signed by SSV and snapshotted. So it must reside on a trusted SIP-protected place. Then launch type says that it must be a system service. So it means that it has a corresponding plist somewhere under system library launch daemons. So it must be started through that definition, basically. And validation category 1 means that it must reside in the trust cache. And we also have a parent constraint, which means is init procs, which is basically launchd. So what this whole category will result in that a process or application which is assigned to this category can only be started by launch day, so you cannot spawn it. It must reside on a system volume or on a trusted place, so if you copy it out, it will not run. And because it's a system service, so launch type 1, you cannot create a new plist, new launchd plist and start it through that, because that would mean that the parent is still launchd, it still resides on the system volume, but it wasn't started as a system service, but some other. And if we look at the binaries who belongs to this category, we will find basically all of the system daemons in this list. Couple of examples are listed here. Now, if we look at category number 2, it's basically a much more simplified version of the previous one. So this is only really a constraint that the binary must be on a trusted place. So we will find here all the regular command line utilities, basically. All these, or ls, or whatever, if you copy them out, they will not work. And we have more of these. Trust cache. So I mentioned that all of this in the trust cache. So where we can actually find this and extract the information. Trust cache is coming from the iOS world, and I'm really not into that space. I found these 3 different trust caches. I didn't investigate what's the difference between them and what each of them means. Probably some people know here better than me. But basically all of these trust caches, and they will have all this information. Now these files are EMG4 files, at least for the second 2, and the OS launch policy data is an IM4P file. Now this is some, I think, compressed or some binary format to store data on Apple platforms. So from the EMG4, we first need to extract the IM4P, P is for payload, file. We can use the PyEMG4 utility for that. It will extract that data. Then from the IM4P file, we actually need to extract the actual data. From that, again, we can use the same utility for that. Now we have the trust cache extracted, and now we can use the trust cache utility to actually parse it, or we can write our own tool. It would be really simple because the trust cache is a simple structure containing the CD hash, the hash type, some flags, and the constraint category. And the category is actually the 4th column, so this. Now, reversing launch constraints. So how we can actually find all these launch constraints and what they actually mean. So launch constraints are defined inside the MFI kernel extension, which is the Apple Mobile File Integrity. Nowadays, it's all embedded in the kernel cache, so I think the easiest way is you download the KDK, the kernel development kit, install it, and you will actually get the raw binary. It's much better than dealing with the cache and extracting the kernel extension from the cache, etc. Once we have the text, we can open it, and there will be a lot of symbols defined in that. They all start with the K constraint category something. These are from Sonoma. They are numbered from 1 to 20. But if we look closely, then 19 and 11 is missing. I'm not sure why they skip those numbers. So those are all self-constraints, and then we have a couple of parent constraints, and we have the category number as well. If we dump it, this is what we get. Now we need to make sense of this. So there is a lot of ASCII, hex-encoded ASCII in that, where you can find all the unauthorized system volume. And I actually started to reverse it. Like I found length, structures, whatever. And eventually I realized that Linus said it in his very first documentation, that it's a DER encoded data. I had no clue what's that. So it turns out that's an ASN1 encoding. It's basically a serialized encoding of structures or data into a binary format. There are many tools to decode it, like there are web tools, there is the Python ASN1 library, so you can just use them and put this structure in and decode it. But a very short crash course on DER. So it's a type length value encoding. First you have a type, then a length, and then the value. So let's try to reverse this hex stream into the stuff we see on the right. So first we have a 70, which is an application sequence. There are some flags as well. So anyhow, it's a sequence. 75, it's the size of the following part. And then we have the data. So it's all color-coded. And then we go one step inside. Then we have O2, which is the type integer. Then we have 1 for length, and again 1 for value. Then we have another sequence with some other flags. Again, we have the size and then the data. And then inside the sequence, we have another sequence. And we can go on. Then we have a string, which is OC, and O3 is the length, and actually 24.6F72 is like the ASCII encoding of $OR. Then we have another sequence, and inside the sequence we have another sequence, and inside that we have a string, and then a Boolean. Interestingly, it's a bit odd for me that, so Boolean is type 1, size 1 byte, and FF is true. It feels odd because when I look at FF, if you think about sign values that used to be -1, false, yeah, it's like, but it's all 1, so it's true, but it's a bit weird, at least to me. And then we go forward, again, another sequence with a string, another Boolean, more sequence, and we can decode it this way. And basically, all this stuff will give us the one, oh, it's not seen. Anyhow, this will give us unauthorized out APFS volume or on system volume and launch type 1 and validation category 1. So, attack mitigation. How does it solve our problems? Again, if we think about the previous exploits, we can no longer copy those applications out and just install a new plugin into their directory, so they will not work. So there might be a vulnerability, but we cannot exploit that. Config-D, again, it must be a system process, so we cannot just run it, and that's it. I think this is a truly amazing engineering effort or solution from Apple to solve many of the logic bugs we have seen in the past. It makes my and some of our others' life harder, but it's part of the game. Now let's go into third parties, which is more interesting. So I tried to collect or wrote about some of the most common third-party attacks, at least I see in the wild reported. I try to read all of the blog posts or write-ups on third-party stuff. And I think there is a theme for the past few years as for exploitation. So there is a bunch of third-party XPC daemon attacks. Both Wojciech and me documented it, like we exploited XPC left and right on third-party, and many other people as well. So like it was very easy. I think a couple of years ago we lived the golden ages of XPC exploitation. Basically, all the XPC services which are running as a root daemon are very dangerous. Because all of these services must ensure that the right application is connecting to them, otherwise that should be refused. Now, the client validation is hard, well, not hard, but not straightforward, especially that Apple doesn't provide a documentation how to do it securely. Apple does provide a documentation how to do it, and they say it's secure, but it's not. So developers follow that documentation, and they don't do the right application. And also for a long time, there was no API to actually make it secure at the first place, unless you use some private APIs. So again, we must use the audit token, as we learned today, for client verification. Now for this, before Big Sur, there was no public API to do this. Now we have, but in the past we simply didn't have a secure way to do it. A client must ensure that the certificate is issued by Apple and signed by a developer. A version check should occur, or we should ensure that the client doesn't possess any dangerous entitlements. I want to talk about this for some reason here, embedded XPC attacks. Embedded XPC, I mean when we have an XPC service inside the application bundle, and normally only the application can call it. So it's not like a system-level daemon. I personally not aware any of such attacks on third parties. And I think it's rare even with Apple binaries, at least based on those which made to the public. I found two which abused these embedded XPC services, but really that's it. And again, we are talking here about third parties really, where I haven't seen any such vulnerability. Electron frameworks, well, I will speed through this. Wojciech talked about a lot. They are just horrible as is, full of TCC permissions. You can inject anyhow you want. Yeah, it's just horrible. But all the Electron exploitation goes through either you provide a command line argument or you control the environment variable. Oh, and DLB injection, I think with the hardened runtime, this is dying out. Unless you must support for some reason like third-party plugins, then developer have to use the disable library validation entitlement, which basically allows them to load third-party libraries. I think they are not so common nowadays, but it's still a thing. Now let's talk about launch and environment constraints for third parties. So when I send this abstract to Patrick, this is what I wrote. So actually, I learned that in Sonoma this feature is coming in June. I was really excited about it because I thought that, hey, this will make third-party applications secure. And then I left for 3 months vacation. I came back. And so originally I wanted to talk about how we can make secure third-party applications. No. Let's see why. So before we go into that, launch constraints, it's really, really, really easy to implement for your application. Like I suck at developing anything, and even I could do that. So there is no excuse not doing that. It's in Xcode. You define a code requirement in Xcode. You add it, and that's it. It's very, very well documented at Apple's website. So actually, I gave this talk last week at Mac sysadmin, and I wrote it up. I published it, and then Thijs chatted me that I might misunderstood something, and I must correct myself here. So there I talked about XPC daemons, as I thought that when Apple talked about launch constraints in their WWDC talk, they refer to XPC daemons. But reading it again, it looks like they didn't. They probably think about the embedded XPC services. And they didn't really meant to talk about the global XPC daemons. So probably it will work. So if you set a responsible process for your embedded XPC services, it will likely work, although I have some ideas there I want to test. But let's say it works. But even if it works, we don't see these attacks. I mean, it does solve a problem, but a problem we don't really have. Now, XPC protection for global daemons. So I actually try to play with this because this was my first understanding. If I can protect my XPC daemon being launched by a random exploit. No. So it turns out that for XPC daemons, global XPC daemons, the responsible process is the XPC service itself. And not launchd, not my process. It's the service itself. It might be right because you can trigger a daemon by watching a path or by network activity or whatever. So it might be right, it might be by design. I'm not sure. I submitted a feedback ID. If this is a bug or a feature, I'm not 100%. But so let's say it's a bug. And the responsible process should be the process who is actually want to talk to this service. Launch constraint doesn't solve the issue because if the third-party application talks to the service, it will come up, and at that point, I can also talk to that service because launch constraint's not in play anymore because it's already up and running. So client validation, secure client validation is the only way to secure an XPC service. So launch constraint will not solve that issue. Maybe they didn't mean to solve that issue, but it doesn't. Now, yeah, Electron application. So I was really excited, like, okay, we cannot do XPC, we can secure Electron once and for all. They talk a lot about why POSIX spawn is dangerous because you can control all sorts of things for your child process, like everything, really. So what they say is that you can, yeah, I got POSIX spawn is dangerous. So you can set to your application launch type 3, which means you can start your application. You can only start your application as an application. So like clicking on it. You cannot type it in the command line and run it. But the open command will also launch the application as an application. And the open command can pass environment variables and command line arguments. So I think we are back to square zero. We cannot protect Electron apps with this because we can control their execution environment. So I think the most commonly exploited stuff is through controlling the application with environment variables or command line arguments. So again, it doesn't solve the problem. Or you can just use the API. There is also another thing, library load constraints, where you can define other team IDs from where you accept different frameworks or dilibs. And I think this does solve the problem with when you need to support third-party plugins. But it also assumes that you are aware of every single third-party plugin you need to support and you know their team ID. If like anyone can write a plugin, then it doesn't really help. So conclusion, I think launch constraints for Apple stuff, it's a great design and it really does solve a lot of the issues. For third parties, I think it's a good start, but I think launch constraints for design more on the Apple box side, and I think it doesn't solve the problems with the third-party software we actually see. It does mitigate some attacks, so I'm not saying it's totally junk, but I do think it doesn't solve the issues we see most of the time nowadays. Library load constraints, I think that can be really useful if you can list all the team IDs. I suggest start playing with that and start using it. Again, it's really easy. Yeah, that's it.